In today's video, we're diving into an essential topic in AP Precalculus: inverse trigonometric functions. Our main goal is to learn how to construct and understand the inverse sine, cosine, and tangent functions. By the end of this lesson, you will be able to explain why these functions need to have their domains restricted to have inverses. And you'll be able to work with these inverse functions graphically and analytically. Let's begin by remembering the most important rule for inverse functions. For a function to have an inverse, it must be 1-to-1. This means it must pass the horizontal line test. The horizontal line test states that any horizontal line can intersect the graph at most once. If it intersects more than once, the function is not 1-to-1. Now, let's think about our standard trigonometric functions. Take the sine function. Its graph is a periodic wave that repeats forever in both directions. If we apply the horizontal line test to this graph, we can see it intersects a horizontal line, say y equals 1/2, an infinite number of times. Here we see a horizontal line intersecting the sine curve multiple times. This shows us that the sine function is not 1-to-1 over its entire domain. The same is true for the cosine and tangent functions. Their graphs are periodic as well, and fail the horizontal line test. This presents a problem. How can we define an inverse for a function that isn't 1-to-1? The solution is to do something clever. We restrict the domain of the original function to a smaller interval where it is 1-to-1. In other words, we only use a piece of the graph. When we restrict the domain, we create a new function. This new restricted function is 1-to-1, and its graph will pass the horizontal line test. Once we have this restricted 1-to-1 function, we can find its inverse. This process gives us the inverse trigonometric functions, also known as arcsine, arccosine, and arctangent. In our next scene, we'll see exactly how we do this for sine. Let's focus on the sine function first. Remember our problem. The graph of y equals sine of x fails the horizontal line test. Here again is the graph of the sine function. We need to find an interval on the x-axis where the function is 1-to-1. The standard, agreed upon interval for this restriction is from -π/2 to π/2 inclusive. We restrict the domain of the sine function to the closed interval from -π/2 to π/2. Notice what happens when we do this. Let's look at the graph again, but only for this interval. This highlighted portion of the graph is now our new function. It starts at y equals -1, at x equals -π/2, goes through the origin, and ends at y equals 1 at x equals π/2. Any horizontal line we draw will only intersect this piece of the curve once. The domain of this new, restricted sine function is -π/2 to π/2, and its range is -1-to-1. Since it's now 1-to-1, we can finally define its inverse. We call this inverse function the arcsine function, or inverse sine of x. This is written as y equals arcsine x, or sometimes as y equals sine inverse x. A key concept with inverse functions is that their domains and ranges are switched. So, what is the domain and range of the inverse sine function? The domain of arcsin x is the range of our restricted sine function, which is -1-to-1. The range of arcsin x is the restricted domain of sine, which is -π/2 to π/2. This means the output of arcsin will always be an angle in this interval. Let's put this into practice with an example. Suppose we want to find the exact value of the arcsine of 1/2. The question is, what is the arcsine of 1/2? When you see an inverse trig function, you should immediately think angle. The problem is asking, what angle, when you take its sine, equals 1/2? There are many such angles, but the range of arcsin tells us we must choose the one between -π/2 and π/2. We are looking for an angle, let's call it theta, such that sine of theta equals 1/2, and theta is within the interval from -π/2 to π/2. If you recall your unit circle or special triangles, you know that sine of π/6 is 1/2. Is π/6 in our required interval? Π/6, or 30 degrees, is indeed between -90 degrees and +90 degrees. So, the arcsine of 1/2 is π/6. It's critical to always check the range of the inverse function. Let's try another one. How about the arcsine of -1? We're looking for the angle theta in the interval from -π/2 to π/2, where sine of theta equals -1. Scanning the unit circle in the fourth quadrant, or looking at the graph of restricted sine, we see that the angle is -π/2. It's perfectly within our range. Therefore, the arcsine of -1 is -π/2. In this scene, we successfully defined the inverse sine function by restricting the sine function's domain to pi 2, pi 2, and we found its domain to be -1 and its range to be pi 2, pi 2. We also practiced using this definition to find exact values. Now let's turn our attention to the cosine function. We'll follow the exact same process we used for sine. First, here's the graph of y equals cosine of x. Just like sine, it's periodic and fails the horizontal line test. We need to restrict its domain to an interval where it becomes 1 to 1. The standard restriction for cosine is the interval from 0 to pi. So, we restrict the domain of the cosine function to the closed interval from 0 to pi. Let's see what that looks like on the graph. This portion of the graph is now 1 to 1. It starts at y equals 1 at x equals 0, decreases to y equals -1 at x equals pi, and is continuous and decreasing throughout the interval. Any horizontal line here will intersect the graph at most once. The domain of this restricted cosine function is 0 to pi, and its range is -1 to 1. Now that it's 1 to 1, we can define its inverse. This inverse is called the arccosine function, or inverse cosine. It's written as y equals arccosine x, or y equals cos inverse x. Again, we switch the domain and range from the restricted cosine function to find the properties of arccosine. The domain of arccos x is -1 to 1, and its range is 0 to pi. This is a very important difference from arcsine. The output of arccos will always be an angle between 0 and pi, or 0 and 180 degrees. Let's work through an example. What is the arccosine of -1/2? We need to find the angle theta in the interval from 0 to pi, such that cosine of theta is -1/2. First, let's ignore the negative sign. Cosine of what angle is 1/2? That would be pi over 3. Since our value is negative, our angle must be in the second quadrant, where cosine is negative. In the second quadrant, the angle with a reference angle of pi over 3 is pi minus pi over 3. So, our angle is 2 pi over 3. Is 2 pi over 3 in the range 0 to pi? Yes, it is. 2 pi over 3 is about 2.09, which is less than 3.14. Therefore, the arccosine of -1/2 is 2 pi over 3. This example highlights the importance of the range. The angle -pi over 3 also has a cosine of 1/2, but it's not in the range of arccosine. You must choose the angle in the correct interval. Let's do one more. What is the arccosine of 0? We need an angle theta between 0 and pi whose cosine is 0. Looking at the unit circle, or the graph we just saw, cosine is 0 at pi over 2, and pi over 2 is in our range 0, pi. So, our cosine of 0 is pi over 2. To recap this scene, we defined the arccosine function by restricting cosine's domain to 0 pi, giving arccosine a domain of -1 and a range of 0 pi. We saw how to find exact values by always considering this range. Finally, let's explore the inverse of the tangent function. The process remains the same. Here is the graph of y equals tangent of x. It's periodic with vertical asymptotes at multiples of pi over 2. We need to restrict its domain to an interval where it's 1 to 1. For the tangent function, the standard restriction is the interval from -pi over 2 to pi over 2, excluding the endpoints, because of the asymptotes. So, we restrict the domain of the tangent function to the open interval from -pi over 2 to pi over 2. When we highlight this section of the graph, we see a curve that starts low, goes through the origin, and goes high. It's perfectly 1 to 1. This single branch of the tangent curve is the part we use. Any horizontal line we draw will intersect this branch at most once. The domain of this restricted tangent function is -pi over 2 to pi over 2, and its range is -infinity to infinity. We can now define its inverse. This inverse is the arctangent function, written as y equals arctan x, or y equals tan inverse x. By switching the domain and range, we get the properties of the arctangent function. The domain of arctan x is all real numbers, from -infinity to infinity. The range of arctan x is the open interval from -pi over 2 to pi over 2. This is the same range as arcsine, but with the endpoints excluded. So, an arctangent's output is always an angle strictly between -90 and 90 degrees. Let's find the arctangent of 1. We need to find the angle theta in the interval from -pi over 2 to pi over 2, whose tangent is 1. From our knowledge of trig functions, tangent of pi over 4 equals 1. Is pi over 4 in the range negative pi over 2 to pi over 2? Yes, it is. Pi over 4 is 45 degrees, which is between minus 90 and 90. So, the arctan of 1 is pi over 4. How about the arctangent of negative radical 3? We're looking for an angle theta in the interval from negative pi over 2 to pi over 2 whose tangent is negative radical 3. First, the angle whose tangent is positive radical 3 is pi over 3. Since our value is negative and the range is negative pi over 2 to pi over 2, our angle must be in the fourth quadrant. The fourth quadrant angle, with a reference angle of pi over 3, is negative pi over 3. Is negative pi over 3 in the interval from negative pi over 2 to pi over 2? Yes. So, the arctan of negative radical 3 is negative pi over 3. In this scene, we successfully defined the arctangent function by restricting the tangent function's domain to minus pi 2, giving it a domain of all real numbers and a range of minus pi 2. We also found some exact values. Let's take a moment to summarize what we've learned. It's crucial to keep the restricted domains and ranges straight, as they are the key to understanding inverse trig functions. Remember, the reason we restrict the domains is to make the functions one-to-one so they can have inverses. Let's recap the three inverse functions we discussed. Here we see a table summarizing all three. The arcsine function has a domain of negative 1 to 1 and a range of negative pi over 2 to pi over 2. The arccosine function also has a domain of negative 1 to 1, but its range is from 0 to pi. The arctangent function has a domain of all real numbers and a range from negative pi over 2 to pi over 2, with the endpoints excluded. These ranges are sometimes called the principal values of the inverse functions. When you are asked to find an exact value, you must always choose the angle from these specific ranges. Understanding these definitions allows us to construct and interpret inverse trigonometric functions. The skill lies in applying the correct range to find the principal angle. So, to recap our main learning objective, we have now seen how to construct the inverse sine, cosine, and tangent functions by restricting the domains of the original functions. We've also practiced constructing and finding exact values using these new inverse functions. Great work today! Keep practicing, and I'll see you next time.